So welcome back. This is the second part of our discussions in week 4 of advanced algorithms. As we promised, in this part, we are going to be developing the concepts of pathwidth and treewidth, which are quantitative measures of the likeness of an arbitrary graph to a path and a tree, respectively. Now, when we stopped last time, we had developed a dynamic programming algorithm for the maximum weight independent set problem on subgraphs of thin grids, which were essentially grids which have a small number of rows. And the question that we stopped with was, what are the kinds of graphs for which the same kind of a DP idea would work? And if you had a chance to reflect on this question about how much can we expand the purview of the algorithm that we just developed, then you will probably find the definition of a path decomposition to feel at least somewhat along expected lines. So it should feel a little bit familiar. But if it doesn't feel intuitive to begin with, then don't worry about it. As we spend time with the definition and work through some examples, it will all start coming together. So let's start with the definition of what is called a path decomposition, which is an essential tool in defining pathwidth. So a path decomposition for a graph is a sequence of what we will call bags. So bags are just subsets of vertices, okay? So it's a sequence of bags. The sequence is denoted x1, x2, and so on up to xr. And as we just said, each xi is a subset of the vertex set. And this sequence of bags must satisfy certain properties for it to be a valid path decomposition. The first property is called vertex coverage. It basically says that every vertex of our graph must appear in one of the bags. So the union of all the xi's is the entire vertex set of the graph. The second property that the sequence must satisfy is edge coverage. So every edge in our graph must have both of its endpoints showing up in some common bag. So for every edge uv, there is some xj which contains both u and v. The third and the last property is probably the most interesting one. It requires that if a vertex appears in some bag, say xi, and some other bag, say xk, where I is smaller than k, I is the smaller index, then this vertex must also appear in all the bags that come between xi and xk. So for every j between I and k, u also belongs to xj. This means that if you look at all the bags that contain a particular vertex, that collection of bags forms a subinterval in this sequence. There cannot be any gaps whatsoever. So this is the notion of a path decomposition. Now notice that there could be multiple valid path decompositions for a given graph. It's by no means unique. In particular, every graph has the so-called trivial path decomposition, which consists of just one bag, x1, which is equal to the entire vertex set of the graph. This, as you can easily check, satisfies all the three properties that we have listed. Now, it turns out that in general, this is not a very useful path decomposition to work with, as we will see in due course, but it's definitely a perfectly legitimate and valid path decomposition. I would suggest pausing the video here and trying to just double check that the definition is clear and work with some examples of graphs that come to your mind and see if you can devise path decompositions for them. This is an exercise that we will do together in a few minutes from now, but if you would like to, please feel free to play around with the definition yourself, just in the interest of getting used to the ideas here. Now, as we said, there can be multiple path decompositions for the same graph. An important aspect of a path decomposition is what we call its width. The width of a path decomposition is the size of the largest bag in it with a -1. Now you might wonder what's the -1 doing there? It does look a bit artificial. And really, it's just a matter of convention and no cause for alarm. It's just to be able to say things like the path width of a path is 1. So as we will see in a few minutes, that's indeed the case, and the -1 helps out with that. So it's really just a harmless convention and just something for us to remember as we go along. Okay, so this is the width of a given decomposition. What is the path width of a graph? As we said before, a graph can have several path decompositions. Each of them will have their own width. So among all possible path decompositions of a graph, we pick the one that has the smallest width, and this width is called the path width of the entire graph, right? So once again, just to be clear, a given graph G may and in general will have multiple path decompositions. So imagine looking at the space of all possible path decompositions for a graph G, and for each path decomposition, well, that's going to have a width associated with it, and we are going to basically pick the smallest width that we see in this space and declare that to be the path width of the graph. Okay, so that's the concept of path width. And to get used to this idea, let's maybe look at a few examples. Okay, so the most natural one to begin with is a path. So we have a path. What would be a natural path decomposition for this? So of course we do have the trivial decomposition, but when we are thinking about computing the path width of a graph, we should really challenge ourselves to come up with a path decomposition that has the smallest possible width. At least when we are trying, we want to keep the bag sizes as small as we possibly can. So with a path, it really offers itself up for a fairly natural path decomposition that only has 2 vertices per bag. Can you find it? Maybe this is a good place to again pause the video and try to work this out for yourself, because we are going to discuss the details in just a moment now. Okay, so hopefully you had a chance to think about this. But with a path, it turns out that the most natural way to form the sequence is to basically take two vertices at a time in every bag, going from left to right. So that would be my first bag. This would be my second. This would be my third. This is the fourth, the fifth, and so on. Okay? Now notice that we do satisfy all the 3 properties that we care about if we actually complete this decomposition here, and let me do that in a minute. And here's the last bag. So you can see that the union of all the bags indeed contains all the vertices, and that every edge is fully represented by some bag. Indeed, the way we designed this decomposition was to pick up one edge at a time, going from left to right. So certainly every edge has found a bag which has both of its endpoints. The third property about all the bags that a particular vertex occurs in forming an interval, well, the bags here are going to be listed from left to right. So in particular, this is going to be x1, x2, x3, x4, x5, x6, and x7. So if you pick any vertex you like, for example this one, that's going to appear in 2 bags, x4 and x5 in this example. And those 2 bags are necessarily consecutive just by construction. So this is a valid path decomposition. It has 2 vertices per bag. So the maximum bag size of this decomposition is in fact just 2, And therefore, the width of this decomposition is 1 because the width of the decomposition is the size of the largest bag minus 1. And this is practically the reason that we put in the minus 1 in the first place. So the width of this decomposition is 1. So the path width of a path is certainly at most 1. And notice that any graph that has even one edge in it must have path width at least 1 as well, because, well, that edge has to go into some bag, and that bag is going to therefore have at least 2 vertices, and therefore the overall width of any valid path decomposition cannot be less than 1. Okay, so the only graphs that have a path width of 0 would be graphs that are empty, that have no edges in them. Okay, so in general, to show that the path width of a graph is at most something, all you have to do is exhibit a valid path decomposition where the maximum bag size is at most that target quantity plus 1. On the other hand, showing that the path width of some graph is at least something is usually a little bit trickier, and we won't be really covering methods of doing that. They often require understanding alternate characterizations of this definition, although sometimes you can reason it out by first principles logic, as we will see with one of the examples that we do. But in general, I'm not going to be talking about methods for showing lower bounds on the path width. Okay, so for a path, however, we are completely sorted because the easy lower bound matches with the upper bound that we have just demonstrated. So that's the path width of a path. What about the path width of a grid, or possibly some subgraph of the grid? Okay, so this was the subgraph of the grid that we were looking at in part 1 this week. And let's see if we can come up with a path decomposition for this particular graph. I would say go ahead and try to give it a shot yourself. I'm going to wait for a second before starting to discuss this. Okay, so if you remember, one of the things that we said about the grids is that the adjacencies only go between consecutive columns. So there is already a natural left to right ordering on the graph that we are looking at here, which is going in this direction and thinking of it column by column. Now, notice that if we just put every column in one bag, then that's not a valid decomposition. And the reason this would not be a valid decomposition is that it violates the second property of edge representation. So that's, roughly speaking, a proposal for a path decomposition. Here our bags are going to be x1, x2, x3, x4, x5, x6, x7, and x8. So hopefully you can see that this is not a valid path decomposition, because although it satisfies both properties A and C, it fails to satisfy property B, which was the requirement that for every edge in the graph, there must be some bag that contains both the endpoints of that edge. So this doesn't quite work, but there's something that's kind of inspired from this that would work, and perhaps you see it already. So if we combine these bags and take them 2 at a time, then we would be fine. So of course, that is going to come at the cost of increasing the sizes of the bags by a factor of 2. But let's say we take x1 and x2 together, then x2 and x3 together, and then x3 and x4 together, and so on. Okay, so if we do the bags 2 columns at a time, then we see that we do in fact meet all the criteria for a path decomposition, because every edge goes between adjacent columns or adjacent rows, and because let's consider an edge that goes between columns I and j. Well, we put xi and xj together because either j is I plus 1 or I minus 1. So there's definitely a bag that contains both xi and xj. On the other hand, let's consider an edge that goes across two rows. Well, those two rows are not only adjacent, they also belong to the same column, and every column is sitting in some bag. So the row adjacencies are also captured by our path decomposition. And it should be quite clear that all the vertices are also covered. The union of all the bags is indeed the entire vertex set. And the last property that we need to check is that when you look at all the bags that contain any particular vertex, those bags are consecutive. But this is just like with the paths. You can see that the bags that contain a vertex appear next to each other, and there are only two bags that contain any particular vertex. Okay, so those are all the properties of a path decomposition being validated with this example. And therefore, notice that the maximum bag size that we have here is 2 times k, and the width of this decomposition is 2k minus 1. So this is a valid path decomposition, but the path width of a k by n grid is not necessarily 2k minus 1, because for all you know, there might be a better path decomposition in terms of having smaller width. That's entirely possible, and it turns out that that is indeed true. You can do better than 2k minus 1. You can actually go all the way up to k, which is almost the number that we had in the first incorrect proposal that we had. We said take every column and make it a bag. That would have actually given you a, if it was correct, the path, the width of that decomposition would have been k minus 1. Unfortunately, that's not correct, but if we are looking for a path decomposition of width k, we are allowed to sneak in one extra vertex per bag. So you're allowed to have bag sizes up to k plus 1, and it turns out that that more or less saves you. So you can still start with every column being a bag, but then you can slowly transition from one column to the next one by adding one vertex at a time, and then possibly also dropping one vertex as your bags threaten to get too big. For example, your first bag could be just the first column and the first vertex from x2, and your next bag could be all of the first column, but now include the first two vertices of x2. Now you can see that this is problematic, and the reason this is problematic is because this now has k plus 2 vertices, which is one too many. So you don't want to do that, but notice that the first vertex of the first column has now in some sense served its purpose in the decomposition. It has shown up, and all the edges that are incident to it have shown up as well. Notice that these cross edges are not really possible when you're working with a subgraph of a grid. Okay, so we can basically let the first vertex go when we develop our second bag. So we can try something like that. So we are picking up two vertices from the second column while retaining the bottom three vertices of the first column. So you hopefully see a pattern here. You can keep sliding over your bag slowly from the first column to the second. In every step, you incorporate one new vertex from the next column while letting go of one vertex from the previous column. I'm not going to work this out in complete detail, but hopefully you have enough ideas to actually construct this decomposition and convince yourself that it is possible to come up with a path decomposition whose width is just k. Now, can you do even better? It's not clear, right? So, of course, the natural path decomposition that had width k we know that that one is not correct, but for all you know, maybe there is a cleverer decomposition that only uses k vertices per bag, right? So that's a question to think about, really. But if you're looking at the full grid, that is, all the edges are present, then it turns out that the path width is in fact also at least k. You cannot do better than this. Okay, maybe you can when you have a very sparse subgraph of the grid, but if you have the full grid, then you actually do need all your k+1 slots in the bag. Now, this is one of the things that is beyond the scope of our discussion to argue this lower bound, but if you're curious, we will have pointers where you can go and find out more, or if you like, this is a great puzzle to think about on your own as well. Okay, so that's the grid and subgraphs of the grid. Now let's move on to an arbitrary looking graph here. Now notice that this is a graph that also seems to have a natural layered structure. So we could, for example, identify these layers here. And we do know that proposing these layers as the bags is not going to work, because that's not going to account for, again, property B, which requires that every edge has both of its endpoints in some bag. That's not going to work. But we could do the same thing that we did for the grid. We could take these layers two at a time and try to work things out. So when you do that, you get ABC as the first bag, BCDE as the second, and DEFGHI as the third. So we have 3 bags, and the maximum bag size is 6, which means that this is a path decomposition of width 5. Now you could ask, can we do better? Is there a path decomposition with smaller width? And it turns out in this example that there actually is, and you can in fact even show a path decomposition where the maximum bag size is 4, so that the path width drops from 5 to 3. Now, I'm not going to work out this nicer, smaller width path decomposition, but a hint is to see if you really need all those 6 vertices in that last bag, or if you can, again, just like we did with the grids, can you do a slow morphing between the bag BCDE and the bag DEFGHI? Can you split up how you bring in these new vertices as you move from top to bottom? So a slower transition will do it, and that will give you a path decomposition of width, well, maximum bag size 4 and width 3. Now, if you're ambitious, you could say, well, maybe I can even manage with 3 vertices per bag. So maybe the path width can be even better. But it turns out that in this case, 3 is actually the best that you can hope for. And once again, this is a lower bound claim that we are making here. So I'm not going to get into it in a lot of detail. But I will say that the reason for this in this example turns out to be that we have these 4 vertices right here, B, C, D, and E, which form a complete subgraph of our graph, which means that they have all the possible connections between them. And it turns out that whenever this happens, there must actually be a bag that contains all of them together. It's not possible to come up with a path decomposition where these vertices are split. Okay, so that forces a bag to have at least some bag in any decomposition to have at least 4 vertices. So the path width, it turns out, is going to be at least 3. And because you can match that, we actually know the exact path width of this graph. Now, I have not argued why all the vertices of a complete subgraph must show up in the same bag. I'm again going to say that that's slightly out of scope, but it's something that you can, at least at an intuitive level, convince yourself of if you think about it a little bit. So I welcome you to take this up again as another sort of an exercise to think about offline. Okay, so let's do one more example, and this will be our last example for now. So let's think about what's the path width of a cycle. Well, a cycle is a path that loops back on itself. So we could start with what we did for a path, which is we tried to put every edge in its own bag. So we would start with this being one bag, this is another, there's one more, this is the fourth bag, the fifth one, and I guess I'm a little bit stuck because I cannot really connect that. I cannot really put down a bag which has those last two vertices, the last edge. So far, I have a path decomposition. My sequence of bags is x1, x2, x3, x4, and x5, right? And so far, this is almost correct. The only problem is that that last edge has not been accounted for in any bag. And I cannot say that, here is a new bag and let's call that x6. I mean, you can, it would fix conditions A and B, you will get vertex and edge coverage, but what's the problem? Well, the problem is that if you look at all the bags that contain the first vertex, that's going to be x1 and x6, and that unfortunately does not form a subinterval of x1 through x6. So if we had to satisfy property C, which is by the way satisfied for all the other vertices that we have here, all the other vertices appear in consecutive bags, okay? However, this first vertex that's been highlighted here appears in bags x1 and x6, and unfortunately that forces it to appear in all the intermediate bags. If we have to fix this path decomposition, make it a valid decomposition, then the bags x2, x3, x4, and x5 will have to accommodate, apart from the two vertices that they already have, this first start vertex here. So that gives us a valid path decomposition where the maximum bag size is 3. In fact, almost all of our bags are going to have 3 vertices. So certainly some of them will have 3 vertices. So that's a path decomposition of width 2. And that's an upper bound on the path width of a cycle. And it turns out that it's also a lower bound. You actually cannot get away without putting 3 vertices in some bag when you're trying to develop a path decomposition for a cycle. Once again, lower bound, so I'm not going to get into the details of this argument, but this is again something that you should be able to convince yourself of, at least at a high level. Notice that when you have a cycle, let's say somebody comes up with a path decomposition for a cycle, say x1, x2, x3, and on up to xr, and they claim that each one of these bags has, at most 2 vertices, and it's a valid path decomposition for a cycle. And well, if that happens, then you can start arguing towards a contradiction as follows. So let's take the interval that corresponds to our star vertex here, right? So that's going to be some subinterval of the path decomposition that's been given to you. Now let's look at the neighbors of this vertex. At this point, it's useful for me to give them names. So let's say this is u, v, and w. Now notice that the interval for v must overlap with the interval for u, because if it doesn't, then you don't capture the edge uv, right? And the interval for w must overlap with, again, the interval for u, right? Now, notice that these intervals cannot actually touch each other. The blue and the red intervals cannot overlap, because if they did, then at the bag at which they overlap, you have a bag that contains U, V, and W, but that contradicts your assumption that every bag has at most 2 vertices. So these are 2 intervals that overlap with the green interval, but they are themselves non-overlapping, and you can extend this argument further into the cycle, and at some point you will see that you will end up with 2 extreme intervals at the ends which must be overlapping because you have to account for that last edge, but at the same time, by construction, they're not allowed to overlap, right? So that means that you don't actually have a valid path decomposition on your hands. Some edge has actually been completely missed. Okay, so that's the spirit of how you would argue that any path decomposition for a cycle actually does need at least 3 vertices in some bag. Okay, I don't know which one, but there must be a bag that has at least 3 vertices, because when you cap every bag size at 2, then you can force a contradiction like we just saw. So this is an example of a situation where you can argue a lower bound on the pathwidth by arguing from first principles, just looking at the definition of a path decomposition and using the structure of the graph. Okay, so that's our final example for understanding the definition of a path decomposition. Hopefully by now the definition feels reasonably clear and familiar. Let's move on from here to talk about an important concept in the context of such decompositions. This is the notion of a separation. Now, a lot of the dynamic programming ideas that we saw last time will actually extend to graphs that have path decompositions of width at most k, and they will translate to dynamic programming algorithms whose running time will be some exponential in k and polynomial in n, exactly like we wanted it last time. And the heart of why these dynamic programming algorithms actually work is really the notion of the separation properties that these path decompositions give you. And as we will see later, this will also be true for tree decompositions. Okay, so let's talk about what these separations are. Okay, so formally, a separation is a pair of vertex subsets of a graph G which cover the entire graph and which are such that there are no edges between a minus b and b minus a. Okay, this definition is definitely much easier with a picture, so let me show you a picture. So you have the graph being split into A and B. It's not a perfect partition. They may have an overlap. But apart from the overlap, if you look at the two sides of the symmetric difference, they don't talk to each other. There are no edges that go from one side to the other side. So the intersection of these two sets is called the separator. The size of the intersection is called the order of the separation. Okay, and the whole thing, this whole picture, is this pair of vertex subsets. That's what we call AB separation. Okay. Now, another useful definition is this concept of a border. So when you have a vertex subset A, the border of this subset is all the vertices that see outside the subset through edges. So every vertex in A that has a neighbor outside of A is on the border of A. Anything that's not in the border of A does not see the rest of the world. All of its neighbors are inside the set A itself. So if we have to tie this back to the terminology that we just learned, imagine looking at the rest of the world. Okay, so everything that's outside of A, that's V minus A. So if you think of V minus A and include the border in it, okay, then that along with A forms a separation where the separator is just the border of A. Okay, I hope this makes sense. It is a lot of new notation at once. Speaking of notation, I should mention explicitly that the border of a set is typically denoted as del of A. So this is a good place to pause and make sure that both of these definitions, the notion of a separation and the notion of a border, are reasonably clear. Okay, so moving on, let's make a claim about a certain separation property offered by a path decomposition. So we claim that if you look at the graph induced by the union of the vertices in the first j bags of the path decomposition, and then all the bags from the j plus 1th bag onwards till the end, if you look at those two vertex subsets, then they form a separation, with the separator being the intersection of the two bags where we chose to split things up. So xj and xj plus 1. So once again, just to reiterate, what we are saying is take a path decomposition, look at the first j bags, take the union of these j bags and look at that subset of vertices in the graph. Let's call this A. And similarly, take all the bags from the j plus 1th bag all the way up to the last bag, the rth bag, take the union of those bags. That's another subset of vertices of the graph, and that's B. Notice that A union B is the entire vertex subset because that's the first property of a path decomposition. The union of all the bags is the entire vertex set, right? So that's what we have. And now we are claiming that this pair AB is actually a separation, and the separator is the intersection of the two bags xj and xj plus 1. Okay, and let's take a look at why. So let's argue this by contradiction. So let's say that there is some vertex in A minus B that has an edge to some vertex in B minus A. So let this vertex in A be U, okay? And because it's in A is the union of the first J bags, so U must belong to one of these bags. Let's call that bag XP. It might belong to multiple bags, and that's fine if that's the case, just pick one of them arbitrarily. Similarly, V must belong to one of the bags between xj plus 1 and xr. Suppose V belongs to xq, okay? V must belong to one of these bags. Again, by definition, we are assuming that V is in B minus A, and B was basically the union of all the bags from xj plus 1 to xr. Okay, so V must belong to one of these bags, U must belong to one of those bags. So now that we have identified which bags U and V belong to, let's also use property B of a path decomposition, which says that there must be a bag that contains both U and V. Now this bag must be somewhere. It's either in the red set or in the green set. By symmetry, both cases work out the same way. So let me just assume that the bag that contains both endpoints of the edge UV is on the red side. Okay, so we have some other bag here. Let's say that's X sub W. Okay, and this bag contains both U and V. But now let's apply property C to the vertex V. Okay, so V appears in XW, V appears in XQ, and W is clearly less than Q, which means that V must appear in all the bags between W and Q. In particular, it must appear in both XJ and XJ plus 1, which means that V in fact belongs to XJ intersection XJ plus 1, which contradicts our assumption that V was in B minus A, right? So hopefully this argument was clear. If not, I would suggest taking a pause and absorbing it once again. This is an argument where we really use all the three properties of a path decomposition. And it's the fact that the intersection of consecutive bags really separate everything on the left from everything on the right. The separation turns out to be really useful when we are doing dynamic programming, because it really means that we can afford to focus on what's going on a bag locally without having to worry about information leaks across the board. So that's something that will become clearer as we do examples of dynamic programming over these structures. We'll see how the proof of correctness is aided by these separation properties that are given to us by these structures. Now, setting up the path decomposition notion was really a warm-up to talk about tree decompositions, which is what is coming up next. We're going to do a quick video as a separate part where we define tree decompositions, and once we have done that, we are going to come back and actually look at an example of a complete dynamic programming solution for, again, the maximum weight independent set, but we are going to do it on graphs that have bounded tree width. I'm going to encourage you to try and see if you can generalize the maximum weight independent set algorithm that you saw for thin grids to graphs of bounded path width, because you already have more or less all the ingredients you need to be able to do that. When we come back, we will be talking about tree decompositions, and then we will move on to solving problems on graphs of bounded tree width.